Hello and welcome to another Hacker 101 video. For this video, we have actually partnered with Alex Chapman, who's one of our top bug bounty hunters on HackerOne, to create some videos around container security with a focus mostly on Docker. So if you don't know Alex, please make sure you go on Twitter. We'll put his link in the description and on the screen right here. You can follow him, give him a shout if you like this video. But let's jump into these slides. We're going to talk about Container Security 101. Again, this is going to be mostly focused on Docker, and we're going to have some labs that you would have to set up on your own, but we'll make those also open source. You can download them, install them, practice everything you learned from these slides, and take it from there. All right, let's jump into it. So as you may have already seen, many environments provide you with a code execution as a service, where the ability to run arbitrary commands or code is not considered as a vulnerability. And some of these environments include CI/CD pipelines, which these are the continuous integration or development pipelines, low code environments, serverless functions, and that sort of environments when you work. You can also see these in websites where they teach you how to code, for example. They let you run your code as a part of the interactive learning module. But the point of it is that it's isolated and it allows you to do it, but it's not a vulnerability. These environments isolate risky processes such as web servers to reduce the risk of exploitation. In these instances, to find impactful bugs, we'd have to go further and investigate how isolated these processes are from interacting and interfering with other system processes. In many instances, containers are used to achieve this separation. In this course, we're going to look at the basics of container security and investigate some methods for finding bugs which may allow us to escape the containers. But keep in mind that many of the topics we're going to cover throughout this course could become their own course and their own videos, so we're going to provide further reading for some of these more complex topics. So let's talk about the first thing. What is actually a container? Containers are very simply processes which have been configured with security controls, and they execute within a given file system image. The security controls isolate the processes so they cannot interact with the rest of the host system, and the file system image gives the container process an isolated file system in which to run. So let's talk about what containers are versus virtual machine. So containers and virtual machines attempt to solve many of the same problems. One key similarity is isolating processes from the host system. Containers achieve this isolation in a lightweight way, with all containers sharing the host kernel. While this approach is more performant, it sacrifices some security due to the shared kernel. Virtual machines virtualize a full operating system, including the kernel, to fully isolate processes. This provides a more robust security, but at the expense of performance. Hybrid solutions also exist, which allow running multiple related containers within virtual machines in an attempt to get the best of both worlds. In this course, as I mentioned earlier, we'll be focusing on containers. However, you should be aware that there are significant overlap in techniques for finding and exploiting vulnerabilities in container systems and virtual machines. In this course, we're going to focus on the Docker container environment on Linux, although you should be aware that other container environments exist and can run on other operating systems. The overall architecture of Docker can be more than somewhat confusing for newcomers, and it doesn't help that every few years things get shaken up. At a high level, what we can call Docker is comprised of four major systems. The Docker CLI, or the Docker command, is a command to interface to the Docker Engine API. The second one is the Docker Engine, which contains the building blocks for creating and managing containers, images, volumes, networks, and more. Then there is Containerd, or Containerd, which is a high-level container runtime, which has graduated to a high-level container management system, which can be used as a standalone like Docker Engine. There's Runc, which is a lightweight container runtime and is the entry point into container execution, which is also used to set up the operating system container configuration. That includes a namespace, the Cgroups, and other stuff, and is the first process to execute within the container PID namespace and executes the container entry point. In order to know what commands to run and the environments to run them in, Docker uses the concept of container images. A container image is a template made up of metadata, specifying default container configuration options and a tarred file system. Container images are often based on lightweight Linux distributions such as Alpine Linux or stripped down Ubuntu. Container images can be pulled from a third-party image registry. For example, you can go to hub.docker.com, or they're built locally using Docker file build files. If you'd like to know more about these, we'll actually put a link down below in the description which is a link to the docs website for Docker's official documentation, and you get to read more about these different images. So in this first example we have on the screen, we're telling Docker to create a container based on the Alpine latest image, and we run the echo world command within the container. If the image already exists on the system, the local cache version will be used. Otherwise, the image will be downloaded from the hub, from hub.docker.com by default, and it will do the same thing. The Alpine latest file system will be extracted, and then the echo hello world command will be executed in the extracted file system image. The second example shows a key aspect of container security isolation. The PS command can only show the process running within the container and not the processes from other containers or the container host. Since containers may be used to run untrusted processes or processes at a higher risk of being compromised, security is obviously a huge concern. One container should not be able to affect another container, either by modifying other container files, running processes in the other containers, or constraining resources available to the other containers. On top of all this, a container should not be able to impact the container host in similar ways. Container security can be broken down in three areas: isolation, restriction, and control. Containers must be isolated from other containers and the container host. The resource usage of a container must be restricted so that other containers and the container host have enough resources to continue to operate. Finally, access to potentially dangerous kernel features need to be controlled for containers as well. In order to prevent one container from modifying files in other containers or on the host file system, container processes are chrooted into the container image file system. Chrooting provides a new root directory for the process, which must include all the executables, libraries, and configuration files required for the process. It should be noted that chroot by itself is not considered a security barrier, but it is an important part of the overall container security model. One of the goals of containers is to isolate processes from one another, so one process cannot affect the execution of another. One way this is achieved is via Linux kernel namespaces, which restrict the view a process has of the wider system. For example, the PID namespace isolates the process ID, restarting process numbering from 1, which means that processes in different PID namespaces can have overlapping PIDs without interfering with one another. So there's a few things I want to cover before we go to the next slide. There are going to be 5 namespaces that we're going to cover for this video. The first one is mount. The mount namespace prevents mounts in one namespace from being propagated to other namespaces. Next one is the PID. The PID namespaces provide processes with the namespace with an independent set of process IDs. Network namespace allows the isolation of network interfaces between namespaces. The IPC namespace isolates inter-process communication methods, for example, shared memory between namespaces. And last but not least, the confusingly named UTS namespace, which allows for different host names on the same system. In this example, we will see the mount namespace and how it prevents mounts from affecting directories outside of the namespace. First, we can see that the content of the MNT directory is empty. So we go to a different terminal, we create a shell in a new mount namespace using the unshare command. And in this shell, we mount tmpfs file system over MNT and write to a file under the mount point. And now if we go back to our original terminal, even though a file was written to the tmpfs mount, it doesn't appear as the mount occurred in a separate mount namespace. Next, we're going to see how the PID namespace isolates process IDs. In the first terminal, we're going to echo the PID of the shell, start a new process, and echo its PID. Now you can observe that the process IDs are relatively high when they're returned, but we're going to go to another terminal now, and we're going to start a new shell. And as you can see, the process IDs are relatively high when they're returned. In another terminal, we're going to start a shell in a new PID namespace using the unshare command. Echoing the shell PID shows the shell is running as PID1, and starting a new process in the background and echoing its PID shows that the new process is running as PID2. The net namespace isolates networking operations. In a terminal, we show the IP addresses of the system and we ping Google to prove we have network access. Starting a shell in a new net namespace in the second terminal, we can quickly see that no IP addresses are assigned and network access is not available. And finally, a look at the UTS namespace. Checking the host name in one terminal shows the host name of host system configured. But if we start a new shell in the UTS namespace in another terminal and we run the hostname command, we show that the hostname is inherited, and we can change the hostname to container and confirm that the change has actually happened. Back in the original namespace, the hostname of host system persists. And finally, we can see that changing the hostname to foo does not update in the host name of an already configured namespace. One of the security concerns with containers is that the root user within the container is essentially the same user as the root user outside of the container. If a container escape were to happen, an attacker who has root privileges inside the container will be able to grant root privileges outside of the container itself. User namespacing and remapping can prevent this by remapping user IDs, including the root user, inside the containers to low privilege user IDs outside of the container. When this is configured, the root user inside the container still appears as the root user. However, if a container escape occurred, the user will only be able to execute commands and access files as an unprivileged user. But please keep in mind that user remapping is not enabled by default in Docker, and at this time it's not compatible with some configurations, for example, privileged containers. The nsenter command allows a process to execute within the specified namespaces of another process. This is really useful when trying to debug namespace oddities. In this example, we execute a long-running tail command in a container, and we use nsenter from the container host to execute the ps command in the tail process namespace. As you can see, this has the same result as if we had run the ps command in the running container using the docker exec command. Control groups or Cgroups are a Linux kernel feature that restricts the resource usage of a process. All kinds of limits can be set on processes, memory, networking, devices, and more. For example, the number of process IDs can be limited, so a process can only create a limited number of processes or limit on the amount of memory used that can be enforced. Any process which is created within a limited Cgroup will not fork or will be killed if it exceeds the Cgroup limits. Keep in mind that Docker does not constrain resources for a container. This needs to be configured on a container by container basis, which means that any container with a default Cgroup configuration could exhaust all available resources, including memory, CPU cycles, and more, in order to deny access to those resources to another container or the container host. And if this is not properly configured, it can lead to system instability, resulting in a denial of service. In this example, we would create a PIDS or process ID Cgroup and manipulate the maximum number of processes permitted to execute within the Cgroup. First, we use the sysfs sudo file system to create a new PIDS Cgroup using the make directory or mkdir and set the maximum number of PIDs permitted within the Cgroup to 1. In a separate terminal, we create a shell in the new Cgroup using the cgexec command. The shell process counts towards a PID count in the Cgroup, and as you can see that the subsequent commands cannot be executed as the Cgroup has reached its maximum process IDs. And now we go back to our original terminal and we increase the number of maximum PIDs permitted to 20. And in our Cgrouped shell, we can now see that the further processes can be created and allowing us to execute commands. In our second example, we would create a memory Cgroup and set a limit on the memory usage for the Cgroup. First, we use the sysfs sudo file system to create a new memory Cgroup using the mkdir command and set a very low memory limit. In the new terminal, we start a shell in the newly created Cgroup. Now, any process which requires even a moderate amount of memory to run will be killed in this shell. We go back to our first terminal and we increase the memory limit by setting a larger value in the memory.limit in bytes sudo file, and we can see that with this new memory limit, we can now run some, but not all commands without them being killed in this Cgroup shell. Despite the isolation and restrictions imposed by Chroot, namespace, and Cgroups, many Linux kernel features could still be exploited by a rogue container to affect the workloads of other containers or compromise a container host. For example, the capnet raw capability controls the ability to write raw network packets, and by default, Docker drops all capabilities except those explicitly required. These capabilities assigned to a container can be identified by using the capsh command, which may not exist within the container by default, but capsh outputs the current process capabilities, as you can see on the screen. In this example, we modify the capabilities of a shell dropping the cap sysadmin capability, and then we observe the consequences. In one terminal, we create a working directory. In our second terminal, we use capsh to drop the cap sysadmin capability and show even without this capability, we're still running as the root user. Next, we try to mount a tmpfs file system on top of the working directory, but we get a permission deny error due to the missing cap sysadmin capability. In our original terminal, we confirmed that mounting the tmpfs file system is possible with the normal capabilities set. Back in our reduced capability shell, we next attempt to unmount the tmpfs mount, but once again, we're denied due to the missing capability. Finally, we show that it's possible to unmount the tmpfs mount in the original terminal with the normal capabilities set. Finally, containers can be further locked down with the Seccomp and Apparmor profiles. Seccomp can be used to restrict the syscalls available to a container. Docker's default Seccomp profile disables access to 44 potentially dangerous system calls, such as those which allow access to the kernel keyring. The Seccomp profile use changes based on the capabilities granted to a container. Apparmor is a Linux kernel security module that can be used to restrict the actions of a process, such as limiting network access or file read, write, execute permissions. The default Docker Apparmor profile aims to be moderately protective while providing wide application capability. On top of the built-in security settings provided, Docker implements a plugin interface to allow users to write custom authorization plugins to restrict the commands and command options that can be executed against Dockerd or Dockerd. However, no authorization plugins are installed by default. To summarize all this, containers are simply normal Linux process trees which have been constrained by various security configurations. Chroot and namespaces isolate containers from other processes on the system. Cgroups restrict resource usage of a container, while capabilities, Seccomp, and Apparmor control the permissible actions of a container. At this point, we have covered the basics of containers and container security. There are so many good resources to help expand on this knowledge. Here are some that I highly recommend you check out. Now let's get into escaping containers. Containers in a default configuration are generally considered to be at least somewhat secure, bearing software vulnerabilities. As an attacker, a particularly interesting attack vector is escaping the container in order to run commands on the container host. Avenues for container escape are generally introduced by the configuration and insecure use of a container in an environment. This section will outline some methods to escape a container in order to execute commands on the container host. It should be noted that many container escape techniques may require root privileges within the container. For this course, we're not going to cover Linux privilege escalation here. However, there are plenty of resources available for this topic elsewhere. Like all software, vulnerabilities may be identified in Docker, Containerd or Containerd, or Runc, which could allow a malicious container to execute commands on the container host. Two notable examples in Runc are the CVE-2019-5962 and CVE-2019-5736. These vulnerabilities allow the container to overwrite the Runc binary on the host system, resulting in container escape. A vulnerability identified in the command Docker cp in 2019 allowed a container to load a dynamic library from the container into the Docker cp process, resulting in the command execution on the container host. In addition to vulnerabilities in the container software stack, any Linux kernel privilege escalation vulnerability, which can be triggered within a container, could lead to a container escape. Linux kernel vulnerabilities are often exploited to elevate the privileges of a low privilege process to those of a root user. However, in almost all cases, they could be modified to change the namespace of a process or increase the capabilities available to a process in order to escape a container. The caveat for this is that due to limited capabilities and restrictive Seccomp profiles of a process within a container, the attack surface for a kernel vulnerability is severely limited compared to low privilege processes running outside of a container. CVE-2019-5736, a vulnerability in Runc, allows a container image to overwrite the Runc binary on the container host. So the next time that the container is started, the backdoor Runc binary is executed, and it allows the full compromise of the container host as the root user. Exploitation of this vulnerability can be achieved by creating a Docker image which runs the host Runc binary as the entry point via a symlink to proc self-exec. When the container is started, Runc sets up the container environment and executes the container entry point, in this case running itself inside the container. During the creation of the Runc process, in the container, shared libraries are loaded from the container file system rather than the host file system. This is used to load a modified shared library, and when it is loaded, it opens a file descriptor to Runc via the proc self-exe symlink and starts a child helper process which inherits the file descriptor. Finally, the helper process opens the inherited file descriptor with write access, allowing it to overwrite the Runc binary on the container host. By default, Unix sockets are used to control the execution of Docker engine and containerd or containerd. Access to these sockets should be restricted to root users only and not accessible from within a container. However, sometimes the sockets will be bind mounted into a container or accessible from the container network. The Docker REST API provides access to all the Docker engine functionalities, creating and running containers, building images, creating volumes, and etc. Newer versions of Docker have deprecated listening on a TCP port without client-specific authentication. However, this option can and will get bypassed. Where Dockerd or Dockerd is listening on a TLS port, valid client certificates must be provided in order to access the API. The lesser-known containerd or containerd gRPC API can also be used to create containers and manage images. The API is rarely exposed to the network, but may be accessed via the default container socket. If access to either of these sockets is obtained, containers can be executed with full privileges and access to the host file system, which could easily lead to compromising of the container host. Next, we're going to talk about privileged containers, which are containers that run with all capabilities and limited Seccomp and Apparmor profiles. Additionally, privileged containers have access to the /dev directory, allowing them to interact with hardware devices connected to the host directly. In privilege mode, a container has nearly all the same access to the host as processes running outside containers on the host. This increase in privileges can be easily exploited to escape the container. One method is to use Cgroups release agent functionality to execute a command on the container host. Another method is to mount the container host file system from dev and identify sensitive files, which could allow for compromising the host. Identifying privileged containers can be done in many ways, including checking the contents of the dev folder for hardware devices, attempting to perform an action which should be blocked by capabilities, such as mounting tmpfs, or reviewing the outputs of the capsh command. It should be noted that any increase in capabilities over the default can lead to container compromise, not just fully privileged containers. One reason often cited for running privileged containers is to allow Docker in Docker, that is running Docker engine itself within a Docker, which is common in CI/CD pipelines. Volumes and bind mounts allow files and directories from the container host to be mounted into a container file system. Mounts can be identified from the mount sudo file. Anything over and above the normal expected mounts in this file are probably volumes or bind mounts from the container host. While mounts into a container are not a vulnerability on their own, if a process from a host or another container interacts with files written into a mount, there may be a possibility of a container escape. As an example, consider a bind mount directory which stores log files from a container process. These log files may get quite large, so the log rotate command could be used to manage them. If log rotate is ran from the container host, it may be possible to create a symbolic link or a symlink in the mount directory which causes log rotate to read a file from a container host and save it to the mount. Vulnerabilities like these are applications and configuration specific, so it can be difficult to identify and exploit. Careful analysis of the processes running within a container can identify if a process outside of the container is acting on files in a bind mount. Now let's talk about network services. Unless specifically configured, Docker container networks are flat networks permitting any container to communicate with any other container and the container host. Network data flows in the container networks can be classified into 3 buckets: host to container, container to container, and container to host. Services in each of these buckets may present different opportunities for a container escape or container to container compromise. In order to identify services on the container network, port scanning techniques may be used. Once identified, the individual service and its use have to be assessed for vulnerabilities. Now let's talk about each of these buckets. Host to container. Host to container. Containers often run network services which are consumed by the container host. Depending on the service, this may provide an avenue for container escape or other attacks. This can be especially prevalent where the connecting system trusts the response from a container service even though the service may be compromised. Container to container networking entirely depends on the function of the container environment. Other containers may provide supporting services like databases for a traditional web application backend, or a container may be running processes from other users like in a build pipeline. Where containers are running the same or similar container images, it can be useful to assess how authentication of network services are performed and whether any information on the current container can be used to compromise other containers. So this bucket of container to host services can actually be put into 2 different categories: intentional services and unintentional services. Intentional services, which may be exposed to a container via the network, include REST APIs and databases and similar things, versus in unintentional services, they include anything unintentionally bound to the container network interface from the host. This may include web management interfaces, metric APIs, databases, key value stores, or the Docker API. So since we are doing this for Hacker 101 and our main focus are bug bounty programs, I want to actually consider these 2 case studies on container escape that were based on real vulnerabilities. So for this first example, it's a multi-container web application escape. The attacker was able to get a command execution or code execution with a low privileged user in the web app container. The logs for this web application were being stored in a bind mountain directory with log rotation happening from a process on the container host. As we mentioned this earlier as one of our examples, they were able to leverage a symlink to a file on the container host, which caused the log rotation to append or link to destination when the next rotation occurred. This could have been exploited to write arbitrary data from the web server error logs to any arbitrary file on the container host, ultimately leading to a container escape. The second case study is the CI/CD container to container networking. This vulnerability started with a command execution on a container running in a CI/CD pipeline. Analysis of the container image identified a key store that included JWT signing keys. In each execution of the build, the signing keys were the same, even across users. The key store was used to authenticate requests to a debug service listening on a high TCP port. Using the signing key, a token could be forged to authenticate to the debug service running on other containers in the pipeline. This resulted in full compromise of other users' builds, as well as disclosing private source code and source control credentials. Again, this isn't a complete course on Docker Escape. It's a good place to get you started. If you're interested in doing further reading, the recommendation here is to look at bypassing Docker auth plugins and using Docker containered for PrivEsc. The links are on the screen. The second one is attacking development pipelines for actual profit. And last but not least is break out of the box, which is also linked. All 3 of them are on there. I will put them also in the description of the video to make sure you're able to extend on this video. Again, thank you so much to Alex Chapman for providing all these content, giving us the slides, giving us a lab for you all to practice on. The labs will be published on GitHub later on our website, so you can go to hacker101.com and look for our Docker resources and put these examples and everything you have learned into practice using the labs that are provided. Hopefully you learned something new about Docker hacking or Docker security. If you like videos like this, please make sure you go to hacker101.com. We have a library of contents on hacking. We also have a CTF platform where you're able to hack on a particular web application. And for every few points that you get, you actually receive a private invitation to a bug bounty program on HackerOne. That's it. See you in the next video.